Hello everyone, and welcome to the last live session within the first International Electronic Conference on Actuator Technology, Material, Devices and Applications. This conference has been organized by MDPI and the journal Actuators. Again, I would like to take this chance to thank our chairs and all the people from the conference committee for making this conference possible, and all the participants for joining us today. Until the end of the week, you still have the opportunity to read and comment all the author submissions presented for the conference. So please look at our webpage for more information. I would like to remind everyone that this webinar is being recorded and that we also have a YouTube live streaming. The recording will be posted on the conference webpage for everyone to watch it as soon as possible. And I will be sharing the YouTube live link through the chat in a few moments. I will now present our chairs. First, Professor José Luis Sánchez Rojas from the University of Castilla-La Mancha in Spain. His research interests cover optical and electrical characterization and modeling of semiconductor devices, miniaturization, design and application of MEMS, sensors and actuators. Our second chair is Professor Tatiana Minav from Tampere University in Finland. She is an expert in electrohydrostatic systems and actuators, cylindred, sensorless position motion control, and in an energy balance and recovery system in off-road mobile machinery. Thank you all for accepting to participate in this session. The microphone is yours. Everyone, enjoy.
Okay, thank you, Anna. Thank you for the nice introduction. I think we are in the last live session, last but not least, on applications of actuators, and it's a pleasure for me and an honor to chair this session with Professor Tatiana Minav. Tatiana, are you there?
Yes, welcome everyone. My name is Tatiana Minav. I'm professor in hybrid drives in Tampere University. And like Professor José told us, we have a last webinar for this conference, but conferences continue. We have a Friday to check all publications and video presentation given by our authors. And our first keynote speaker is Elena Lomonova, with the talk Paradigm and Electromechanics, Decoding the Physical Complexity of High Precision Positioning System. Elena have been studied extensively electromechanical and control system in Moscow Aviation University in Russia, and he graduated as a PhD in 1993 on research of autonomous power and control system for vehicle with laser equipment. From 2009, she is appointed as full-time professor in Eindhoven University. She's a chair with a focus on the fundamental and applied research enabling energy conversion theory, methods and technology of high precision, automotive and medical system. Elena, floor is yours.
Elena, the screen is yours, in fact.
Thank you very much for nice introduction, Mr. Chairman and Miss Chairman. Chairwoman, sorry. Good morning, everyone. It's my pleasure to join this presentation and to share with you some achievements and ideas about the new paradigm in electromechanics, while we are going to discuss how to decode the complexity of the physical systems, especially in the area of high precision position systems. First of all, I would like to tell a few words about the group of electromechanics, and might be the main idea is to introduce the lecture today from the words of Michael Faraday, that the lectures which really teach will never be popular, lectures which are popular will never really teach. Also, using the words of very famous physicist Leo Landau, who has a Nobel Prize in Physics in 1962, a method is more important than a discovery, since the right method will lead to new and even more important discoveries. I will talk today about methods and might be even simplification of the very complex, high precision systems. To avoid the complexity, we are going to decompose the electromagnetic system in two main elements or components. It is a permanent magnet and the coil. Permanent magnet is the source of the flux and the coil is the source of the flux. And how these two bodies are influencing each other and creating for us the force product or torque in different shapes or topologies of electromagnetic or electromechanical actuators. The permanent magnets can be modeled by means of equivalent magnetic surface charges, and the coil can be predicted the behavior of the coil by force and torque obtained from the Lorentz integrals. It's amazing, but I'm not talking about finite element analysis. I'm talking about simplification of the possible analytical or semi-analytical description of the behavior of these flux sources in a complex, high precision systems. Simplification, especially necessary when we are working with open boundary conditions. Instead of routine or finite element methods, which pushes us to calculate by days, weeks, or years the complex structures with the open boundary conditions, we could come to very elegant description, simplifying not only description, but also saving a lot of simulation time and making routines of the optimization of the design more elegant and light. Results are extended to full magnet array. If I'm able to describe the behavior of the permanent magnet or the coil, and array of the coil set by translation and rotation. We are looking at the several examples, which I'm going to use today. The first example will be related to the so-called planar stages. What does it mean, planar stage? It is a planary flat platform which is able to move in XY plane and also be able to move freely in Z direction. Mover could be magnetically levitated, and the first concept, which was introduced by Xavier Moto in 1968, has a lot of changes and evaluations. Stepper motor was at that time with air bearings. The modern planar motors are the subject also for the combination, not only of the propulsion and freely movement by means of bearings, but instead of air bearings or roller bearings, we could introduce the combination of the propulsion together with the free levitation. Free levitation means that we do not have any assembly of the magnetic bearings. Permanent magnet planar motors are applied in a semiconductor equipment, and you can recognize one of the semiconductor machines for production of the wafers as a basis for the production of the integral schemes with a very accurate position and very high throughput. To give you an impression on the next slide, you will be able to see the peculiarity of the movements and the essential steps of the production of the wafers. This equipment is used in semiconductor equipment, integrated magnetic bearings, and also in air bearings, for example, for wafer dicing. And this is the sample of the lithography machine, which the price of which is equal to the price of the aircraft of the middle class. So it's about 120 million euros. So the body of the machine, and what you can see right now over here, will be increased the size. It is a stage, wafer stage, with the movement of the wafer on the top of that. Let's take a look a little bit more on this device to see the heart of that machine. So we have a very intensive arrangement of the lenses or mirrors for focusing the images from the reticle stage, which is identical to the wafer stage, and to produce the images to the wafer and fast change of the reticles on the top of the machine allows us to intensively change the production of the images on the wafers. Besides that, it's not only production of the images of on the semiconductor platform, but also inspection of the wafers after several steps of illumination of the images. If we look in a very simple way how it is arranged, so we have a light source, we have set of lenses, we have so-called reticle stage, and then we have again set of lenses and wafer, which has to be moved with accelerations up to 400 meters per second square, and with accuracy position up to 1.5 nanometers. The additional complexity of the system is associated with the fact that we have to operate in vacuum conditions. So no heat sources should be placed in the vacuum. So the movement of the wafer will be in the planar stage. And as I mentioned before, it has to be freely supported and have chance, the platform itself, which is supporting the wafer, to be able to levitate. If we're looking at the planar motor, which is introduced by the black color here schematically, so we have a wafer on the top of that, and this is a long stroke electromagnetic planar actuator, so combination of permanent magnets and the coils only. Any inclusion of the ferromagnetic materials should be excluded because of the fact that ferromagnetic material is the subject for the forces between the moving body and the stationary body. So we have to avoid by all means the attraction force, which is rather intensive or high. So the integrated circuit is imaged by means of the light to the wafer from the reticle, and adjustment, short adjustment of the in a nanometer range. It is done additionally by the so-called short stroke actuators. The process of the production of integrated circuit microprocessors is very accurate and fast positioned, and the position of the wafer is crucial because any discrepancy in or inaccuracy in the position of the wafer will bring to the mistakes for the elimination of the images from the mask of the reticle. Typically, it is a so-called dual stage topology for 6 degrees of freedom position of the wafer. So dual active stage, it means long stroke and short strokes. A long stroke moving in the planar way, and short stroke are adjusting the wafer at the final position. So how it can look like? So this is again the image of the machine, lithography machine produced by in Veldhoven, the Netherlands, by company ASML, the leading company in the world, occupying the 80% of the market of the lithography in high-end products. And the image how the processing of the wafers is going on, but mainly with the focus on the planar actuation, is given by the following movie. So what do you see? The double stages with the wafers, and then one wafer is illuminated currently, and another one, left one, is a subject for the inspection of the quality of the images on the wafer. And now it's coming the crucial moment. Please take a look, because these two planar actuators are aligned, and then it's very fast exchange of the planar motors or wafers is going to change the jobs for illumination and inspection. If we are looking at the possible configuration, so it could be done by combination of linear motors, linear permanent magnet motors, so-called H bridges, which can move along the y-axis and along the x-axis, and the second H bridge, and the same procedure can be done by processing the wafers and changing the wafers for the inspection. However, this is a very bulky construction. It's a subject for many additional parasitic phenomena like backlash or friction, and to eliminate that, the concept of the planar motors, especially without cables, and it means that we have to eliminate cables for the delivery of the power and delivery of the cooling of the actuators. We are thinking about the concept so-called magnet levitation above the coils, which will be placed on the stationary platform, and the small platforms with the permanent magnets on beneath of this image will be freely levitating on the top of the coils. Let's take a look at how it's can operate and compare the performance of the similar movements with the big difference that this system cannot operate in the vacuum conditions, and this is the system which can not only operate in vacuum conditions, but is free of the many parasitic phenomena associated with the mechanical slabs and heating. So if you look schematically on the movement of the planar stage, you can see that ideally it is a permanent magnet platform. With the gray color are the permanent magnets assembled in a Halbach arrangement in X and Y plane. And then on the bottom, you can see the set of the coils, which are distributed also in the X and Y direction. So if we look at the movement, so it is could levitate, could move along X and Y axis, but it's also a subject of the tilting around or rotational, small rotations around the Cartesian coordinate systems. So it's purely 6 degrees of freedom system magnetically levitated. If we look at this image, it is give you the impression about the full movement in XYZ plane, and with the wafer on the top of that. And of course, it's a slow movement. In reality, it is significantly fast, that sometimes even you cannot recognize by the eye due to very high accelerations and jerks in the system, the processing and positioning of the wafer stage. If we compare two concepts, one concept is with the coils on the top of the permanent magnets. That concept we call moving coil concept, and on the right side we see a so-called moving magnet concept above the coils. There are physically they are similar to each other. However, the main physical difference that the force in the permanent moving magnet platform is acting on the coil volumes, and the torque arm is larger and position dependent for the moving magnet planar motors. By other means, if I move this platform, the coil arm, the force produced by the coil, or the arm of the force produced by the coil, is varying in time. So it is an amplitude value, and this brings to the instability or the oscillating along the XY plane. So modeling and control of that system is much more complex in moving magnets case in comparison with the moving coil concepts. However, the moving coil concept is the subject of adding additional mass because of heavy cables for delivery the power and the liquid for cooling. Let's take a look now and compare the performance of these two actuators. This one on the top, it is so-called moving coil, and what you can see, the vectors of the force, which are created by the individual set of arrays of the permanent magnets and associated colors of the current, which we have to deliver from the power electronics, from the power amplifiers towards the coils to provide a constant force vector. And in this example with the moving magnet, we can see that to establish the constant force vector during the movement, we have to apply very non-sinusoidal shapes to the individually powered coils in the stationary assembly. So this leads to many research questions which have to be tackled during the pre-design and predefining especially the control schemes in real-time operation of that systems. Besides, we have additional complexity, but let's take a look and compare further. So what we see, again, the assembly of the permanent magnets on the stationary world. So it is moving coil planar motor, and mover is presented by orthogonally positioned sets of three-phase coils, 4 sets. They can be expanded or extended in the X and Y plane, but this is just a single cage or single set to demonstrate the performance of this configuration. So what we have to additionally consider that it will be additionally heavy structure on the top of that to avoid the bending of the arrangement of the coils, and additional complexity or unpleasant element of the total system, its arrangement of the power cables and cooling cables, as I said before. On the top of that, additionally, we have so-called short stroke actuators. It's voice coil actuators which are positioned accurately the wafer during the operation. And wafer is positioned on the top of the whole global structure. So it is moving in the following way. So it's a heavy dual structure, and look at the behavior of the cable. It's significant disturbance which has to be compensated by feed-forward or advanced control methods. If we are looking at the movement of the permanent magnet array on above the coil, so it's inverted structure, we have to predict and see the behavior, not only electromagnetic one, but also thermal, mechanical, and commutation of the coils, which will be responsible for very irregular shapes of the forms of the current. So force and torque distribution on the magnet planes is obtained from electromagnetic model, and force and torque distribution and currents are very highly position dependent. Additionally, we have a mechanical model which has to be coupled with the electromagnetic model, and mechanical model can predict the deformation, and we should compensate the possible deformation of that seemingly flat structure by so-called over-actuation of the produced by the coils to reduce the deformation. So we can apply the forces from individual coils to compensate the bend and mold and to make it flat back. So to show you how it is looking, the first example was demonstrated with the bend and mold, and compensation is coming by associated additional coils which compensate the the bending. The colors which you see over here around for each coil are introducing also the thermal stress. So because of the different amplitude of the current in this structure, individually fed by power amplifiers, which can be, of course, grouped by means of the multiplex solution to the group of the coils powered by single power amplifier. But due to the necessity to compensate the bending modes, the stresses or thermal distribution is quite different. So it is motivating us to come to the additional structure model which should be coupled with mechanical and electromagnetic models. So altogether, temperature distribution is calculated from the current distribution, and overactuation additionally allows reducing the maximum temperature and increasing maximum acceleration. So the complexity of the system comes to the complexity of the model, but if we are modeling very elegantly the permanent magnets and coils in a very simplified way, this complexity could be easily compensated by means of simplification of original electromagnetic model. So first of all, we calculate the force and the torques, then we define the commutation of the coils, then we are looking at the mechanical performance and the bending modes, and then coupling with the thermal model dependent on the temperature. So all of them are operating in the simultaneously. So it's multi-scale, multi-physical model, which gives the input for the advanced control systems. So which shapes of the coils could be considered as the candidate for the different structures of the planar mode? It's so-called herringbones planar actuators. It is permanent magnet advanced shapes with orthogonal distribution of the coils, or just circular coils. All these concepts are developed in combination with the companies and realized in real operating setups. So if I compare all mentioned concepts, they have certainly different properties and pros and cons. So the herringbone, the rectangular orthogonal shapes or circular shapes, if we are looking at this set of the pros and cons, are the subject of good acceleration, accuracy, but subject to the strong deformation. Another configuration is suffering from the limitations in acceleration, but is accurate and stable with respect to deformation. The last one is poor in terms of acceleration, accuracy, but very stable in terms of deformation. So how to couple these three concepts and come to the new solutions? This is a challenge for us, but beforehand, I'm trying to show you the first generation of the planar motors realized in our laboratory. So what you see right now, the preparation of the experiment when the coils are placed of the planar actuator on the stationary part, and this aluminum block is to that aluminum block from beneath the permanent magnets are glued. So the system can show the different movement, and you can recognize movement in Z direction, then movement in along the other axis, and X and Y directions, then it will be shown the movement around the axis, and then of the Cartesian coordinate system, and then performance during the movement. What you see as a mechanical carcass here, let's call it like that, or attachment, It is on the stage of the training the planar motor to avoid the collapse, because the experimental verification at the university has to be prevented from the collapsing of the planar magnetic plate towards the coils. The forces between the magnetic plate and the coils are in the range of 20 kilonewtons. This is a very light acceleration, only after up to 14 millimeters per second square. The next generation of planar motors is realized over here, so we can see the assembly of the structure, or zooming to the arrangement of the configuration. So it's still herringbone coils with the magnet plate arrangement of magnet assembly on the top of that, and the movement or performance of the planar motor can be easily considered here with the recognition of the forces acting from individually powered coils on the top of the permanent magnets, which is exactly shows the heterogeneous character of force distributions on the structure. So another concept which is a further step on development of planar motors, it is a development of so-called multi-level contactless motion systems based on the top of the planar motor. We are positioned additionally the actuators and reaching the mechatronic system with 8 degrees of freedom. So first of all, it's showing you how the platform operates, and the robot manipulator is placed on the top of the planar motor. So it is 6-door planar actuator together with the 2 degrees of freedom motor, because it's moving in the linear plane and in the rotary plane. So additionally, we have a wireless delivery of the power to the actuators, which are placed on the top of the platform, and wireless communication. So it's 3 types of wireless transfer of energy, propulsion, and data are done within this innovative robotics setup. The second example, very quickly, is the so-called advanced vibration isolation systems. It's so-called gravity compensation. Suppose you are going to do very accurate wafers in your systems, but how to isolate the moving tables of the planar motion from the disturbances even of the neighboring people, or sunsets, or influence of the sea, even the gravity forces which are acting in the world are acting on the bring to the certain very disturbing vibration. So it is a subject for microscopy, lithography, precision systems. Occasionally, it is possible to do just by passive weight, including imposing the permanent magnets only, which can passively, without applying any additional energy, to compensate the micro vibrations. It is should be done for large vertical force, position independency, low energy consumption, micrometer position accuracy, and no memory effects. So if we are looking at the vibration isolation system, generally, so it is a sprung mass with certain springs. And if we are looking at the behavior in ZT plane, we can see with respect to the flow how the sprung mass is behaving. So the gravity compensation should be arranged with the minimum stiffness K, and with the So, and with active vibration isolation. So altogether, we have to realize by means of ordinary permanent magnets only. How to arrange that? Is it possible or not? So magnetic gravity compensation is the subject of acting two fluxes or produces by the permanent magnets in a vertical direction with repelling force and or repulsive force in z direction when the stiffness is more than 0, and the attractive when stiffness kz is less than 0. So following the next discussions, we can recognize that it is horizontally unstable, small active forces are exerted, and high force density can be provided. What should be done? First of all, magnet modeling contributions in 3D field equations and extension from rectangular shape of the modeling the permanent magnet by means of charge, 3D charge modeling approach, to the triangular magnet surface and predicted 3D interaction equations and extended force equations for position, defining the position sensitivity. So arrangements of the permanent magnets, according to the Shaw theorem, are unstable if they are not framed. So, and additionally, we have to reach main objectives, high passive force and low position dependence. If we are looking at the permanent magnets acting with respect to each other, such an arrangement gives us the high passive force but low position dependency. If I go further away, position the magnets from each other, we will have low passive force but low position dependency. How to manage these things and to work and with high passive force and with low position dependency? Very simple. We can think about vertical arrangement with a certain shift of the permanent magnets with respect to each other, and that so-called stack topology with air gap. Why we are shifting them? Just to produce as much force as possible. So the directions of the force vectors are indicated by the following vectors, and stacking them further vertically, we can reach the certain force and reach the certain position dependency. Mirroring them, we can think about the moving part and the stationary part. So think about rotor and stator like electrical machine without any additional arrangements. So we can do the symmetry, reduce the air gap, and minimize the torque arms which are subject in this situation. So this is the passive gravity compensated design. So, and how to arrange that stability between the neighboring parts of the stacking structure. It is a multiplication of the sections, and one section was shown to you. So this is one leg, another leg, third, and the fourth one with the similar arrangement. So cross shape, it is of the gravity compensator with purely permanent magnets is recognizable on that graph or this picture. And we have realization of this gravity compensation in the following format, which allowed us to levitate the mass or weight of 700 kilograms. So magnetic vibration isolation systems could be of that shape. They could be planet tilted, cylindrical, spherical ones, and the design requirements bring us to very accurate gravity compensation prediction of the force with low stiffness and accurate B field predictions. All of them are the subject for unbounded boundary conditions. The third example, very short, it is realization of the actuator and the gravity compensator for so-called multi-degree of freedom actuator and gravity compensation for the arm showed for the joint of the arm for assistance of the arms of the disabled people, and the actuator should provide the movement in the flexion, horizontal flexion, and rotation. Is it possible to make that by somehow, without stacking the actuators, to improve the life of daily living at least 3 degrees of freedom, given the people chance to make to operate with their disabled arms? So we will think about single actuator to avoid bulky arm supports, no predefined sequences of rotation axis, and most torque required to compensate the weight of the arm. So it is possible, and it is realized by means of the so-called spherical actuator and embedded gravity compensator, because spherical actuators are the subject of a very low torque, and if we compensate the gravity, then we solve the problem of the very low torque of the spherical actuator. So spherical actuator consists of several embodiments. So it is actuator itself, so you can see the aluminum supporting structure, 12 single phase coils, permanent magnets arrangement, and decoupling iron back iron. Why? Because we are introducing additionally passive gravity compensator done by this way without a hemispherical permanent magnet, inner hemispherical permanent magnet, and supporting structure compensator. So overall, we have realization of such spherical gravity compensation, which provides all desired by specifications movement and vertical motion, horizontal motion, and the realization of the prototype with the simplification of the structure and with all desired characteristics obtained by the customer. So it leads me to the conclusions, and advanced electromagnetic planar stages, active and passive anti-vibration systems could be fully based on interactions of the coils and permanent magnets. High precision electromagnetic systems require very accurate model predictions, simplified. Parasitic forces and torques may have a high impact on system performance, but if we can find the tools or instruments to decode this complexity and bring it to the very simple solution, it would be very nice approach. And 3D FEM analysis is very slow and may provide insufficient detail in large linear structures. And then analytical tools are an alternative in this paradigm of the new electromagnetic or electromechanical solutions. I would like to finish my presentation with the nice words of Niels Bohr. Prediction is very difficult, especially if it is about the future, especially nowadays. Thank you very much for your attention. And at the end of the lecture, I would like to express my special thanks to all doctors, but former PhD students of our group who contributed to the success of these projects during several years of activity of our laboratory. Thank you very much for your attention.
Okay, thank you. Thank you, Professor Lomonova. Thank you for your nice talk, a nice, interesting talk. I think we should have prepared at least virtual applauses, but well,
thank you very much.
It's a little bit cold, this virtual session.
Thank you.
So we have some questions, I think. We have one question about resolution. And I think it's about you mentioned 1 nanometer resolution, 1 nanometer I think in the short stroke. So this 1 nanometer is
well, basically you are right, but there is a trend to come in 1 shot to at least to 5 nanometer accuracy already by means of the planar motor by long stroke.
So in the case of the long stroke, which is based on the magnets and so on, which is the resolution in this case?
5 nanometers, and the
5.
final tuning up to less than 1 nanometer.
Okay, okay. And I don't know if there is another question, maybe from the audience.
I think it's a similar question.
Okay, I have one more question. In fact, about the feedback in the position. So how do you actually arrange the feedback for this positional precision? Is it based on optical stuff, or?
Yeah, it's evaluation of many types of the sensors. At the beginning, we were using the eddy current sensors and capacitance sensors, and then we moved to the interferometers, laser interferometers, and then we introduced on the top of the system multi optical laser system with tracking the points.
Mm-hmm.
So
okay.
It's up to 25 points of the tracking, the position accuracy from the top of the structure.
Okay, so it's quite
but
challenging.
Along the periphery, it's also the lasers interferometers. If you had seen that, maybe I didn't highlight that, but the block is done as a piece of mirror.
Mm-hmm. Okay, it's quite challenging from the point of view of control. Yeah, very nice.
Yeah.
So if, sorry, any?
Maybe one question, actually we got one question more.
Mm-hmm.
Oh no, that's already answered. Question, I think it's a very expensive machine, a lot of challenges, a lot of advantages you demonstrated, but what about energy consumption compared to conventional machine?
Well, it's the same like aircraft. The energy consumption is horrible just to fly to the United States, especially if you need to fly very fast and compare with Concordia. So it was to translate on the language of aircraft in Concordia, it was consumption of the gasoline or kerosene actually, 1,000 liters per person, per passenger. So similar in these machines, if you want a slow movement, you will not consume energy. If you want a very high acceleration, of course, you will meet the problem. In these actuators, we are in lithography machines. It is 1.5 megawatt power used for cooling, for optical, for lasers, for actuators, because what I showed you, it's only a single example, but that machine consists of 800 actuators and 1,000 sensors.
Okay.
But if you want to have very advanced mobile phone, you have to pay for that.
Yeah. Mm-hmm. Thank you very much, Elena. We are moving forward to.
Thank you very much, likewise, and I wish success to other keynote speakers.
Thank you.
Thank you, Elena. Have a good day.
Have a nice day.
And we're moving forward to our next keynote speaker, Torben Ole Andersen. He is a professor in Department of Energy Technology in Aalborg University, and he is the head of section Fluid Power and Mechatronics system. His research include control theory, energy usage optimization of fluid power component system, mechatronic system design, and control of robotic system. In particular, interest in wind power, wave energy, offshore mechatronic system, autonomous and condition monitoring. His talk is entitled Small Fluid Power Actuators for Digital Displacement Units, Linear Pump Control Drives, and Exoskeletons. Torben, please.
Thank you very much for the introduction. Sorry for the muting here. Now I try to share the screen, hopefully. Well, yes, my speak is about a small fluid power actuators for digital displacement units, linear pump control drives, and exoskeletons. I was a little bit confused about the time I had because as it is stated, it's a keynote talk, but and that should be 40 minutes, but here is only half an hour. But I guess that's okay. I have a lot of slides, but I think that go into detail in all these topics anyway is simply too much. So to put in the conclusions part, the presentation will involve many of things more in detail. Of course, you can then return and ask some questions about that. Yeah, here's an agenda for it. First, I would like to just introduce shortly the environment we have in Aalborg, some of the applications that we have been working. And then, as stated in the title here, I will look into digital displacement units and the linear pump control drives and further developments. And there, I hope that I can talk a little about these exoskeletons, because they are very interesting in small actuators. So the topic here is completely different, I must say, from what we have heard until now. In Aalborg here, we have 3 campuses of Aalborg University. One in Aalborg, it's the main place. Then we have some minor places in Copenhagen and Esbjerg. And if you look at the Energy Technology Institute, it's actually a little bit strange institute, because we cover everything from energy production, distribution, consumption, and control. So it's a quite huge institute here in Denmark, and in many other places, I think some of these topics would be divided into different institutes, but that's also a great main advantage, because all the technology we have in-house and don't have to ask other people around. The way that we organized is that you see that we have different sections above the Department of Engineering: electrical power, thermal energy, power electronics, fluid mechanics, electrical machines, and then of course the most important one, fluid power and mechatronic systems, where I belong. And we are about 250 people, so it's a quite big. And the way that we organize is that we put it up, as we see here, over here, in some research programs. And then the idea is that all these research programs, and that they are moving more or less into mechatronic area, of course, can take input from all these sections. We don't have to collaborate with so many people outside, and it makes it much, much easier to get all these research programs. But if you go to the fluid power and mechatronic systems, the section that I belong to, here the key competences are we actually try to cover most of what is in the fluid power, both on system and component levels. This is not any longer just a mechanical device, of course, we know. So we have to move into the mechatronic systems also, and take into account also electronics and control and so on. And I guess that we are the section that has the most advanced control, so that belongs to us. It's a model-based design. We really say that no trial and error, everything should be modeled. We also have moved a little bit into tribology. We had a big research project where we found out that that might be a good idea. So we have put that into our competences. And of course, digital fluid power. I see it like in the car industry, we have these hybrid cars, but eventually it will be electrical. And I also guess that the fluid power future is within digital fluid power. Then, of course, when we have moved into putting into some electronics into components, and the lifetime also has increased for approximately 10 years for fluid power components into, if we go into wind turbines and the wave energy, at least 20 years. And all this electronics coming in, then fault diagnosis also is a new topic we have to look at. Sometimes if we put into more modeling and have this mechatronic design approach, of course we get more parameters, and one might think that, wow, that's a good idea, then we can model everything. Yeah, but if you have many parameters, how to choose these ones? So optimization is a vital element. Just some examples here. This is for the research program, Fluid Power for Renewable Energy Applications, where we have until now mostly looked on the wind turbines and the power takeoff system for wave energy. And I guess some of the buzzwords here are a little bit the same, what we're trying to do. You can see them on the left here. But up here, it's a yaw system, fluid power. And down here is also looked at some of the wind turbine and we have some of the actuators. So it's in different scales we are looking at. The mission here, of course, is that we will look into the highest international level, and focus has now been in this research on wind turbines and wave energy converters. And we have tried to put into this DDT, discrete displacement technology, to put up the efficiency and the controllability. And so the main focus there had also been in designing control strategies for these systems. But okay, what sets us apart down here? Well, I must really say, if you visit all we have, it's really, really world-class fluid power laboratory facilities. We have not many places in the world, I think, have so nice laboratories as we have here. And it's almost new equipment all over the place, and it's a very, very good environment. So we also sets us apart is that we will test everything we do in the lab. That also this problem-based learning is also part of the University. And of course, that's also an element there that we should go to the lab and really test what we are doing. So we try to combine really this gap between high theoretical level and then some practical issues. Well, if you go for the first part here, as I said, is a discrete displacement technology. It has really been a hot topic the last 10 years. I think that many fluid power institutions, they all do something about this one. And it's in transmissions, both for vehicles, wind turbines especially, and so on. And we were very early. And you see this small motor over here. It was actually 2 students in an 8-semester project who developed our first small DD motor. And the results were very surprising. Noise level was low and efficiency was very high, but unfortunately at that time, I guess it was in 2004, something like that, we didn't have the money to continue. But now we have taken it up again. In the wave energy, we have had a big project running there with a company called Wavestar, and you see over here the name on here, and it was built on some very few of these elements in here, weighing 16 tons each. And then we looked at multi-chamber cylinders. A multi-chamber cylinder has the advantage of the potential for being very efficient. And it's like if you look at what you call secondary control in for rotary transmission, you would typically have that you can, if you have a constant pressure, you can change the displacement and then have a variable torque. That is not in general possible with a linear drive. But having these multi-chamber cylinders here, it'll be somehow the same, that we can put up the force in different discrete steps. And that's one of the advantages by doing this one here for the Wavestar. Here efficiency is completely vital. It is difficult to get a high efficiency here. So the power takeoff system has to be very, very efficient. It's a little bit strange system here because, of course, F multiply velocity is a energy, but if you have this floating element down here, it is too light. It'll just follow the waves, so there is no force in it. And opposite, if it is too heavy, the waves will just flow over it, and you will have no velocity. So there is a compromise inside. So it's not that easy actually. So sometimes you actually have to put in some power into the system again to get more power out. We have a full scale. It's not just a drawing here. We actually have a full scale equipment of this one in our basement, and now we are considering not only more testing it for wave energy. We still are hoping to do that a little bit more, but also in general to test it for multi-chamber cylinders with on-off valves. I'm not going to this. This is just an example of where we did it for the yaw system. Of course, there are some nice way to do that with a fluid power instead of a gearbox and so on. It's simply just more robust. and the fatigue reduction when can be used. We have also worked together with a company in Denmark for a load emulator for wind turbine nacelles. And you can see the size here down here. It's very, very huge. And there's a hexapod here with 6 actuators. And some of these disturbances are up to 10 to 20 meganewton meter. So it's some huge. This can reduce the testing for up to a factor of 10 at least. So it takes still half a year to test such a system here, but it might take 15 years if we did not do that. So here are some other machines that could be benefit from digital displacement units. Of course, these big vehicles here for the transmission. We have a larger project running with in Norway with about these knuckle boom cranes. There's a lot of transmission in this one, and of course this one here has been a test bench now for some years. Every people try to do something about the efficiency in these kind of loader machines. Here we have why we are doing it, and it was actually introduced by a company Artemis in England first. And you see here the digital displacement units can have a very high efficiency over a relative large area, where typically fluid power has an optimum somewhere, and then it degrades drastically when you have partial load. And you see that if you have efficiency of 0.6, for example, and you have a transmission, of course, these efficiency multiplies. So 0.6 multiplied 0.6, very, very low, very fast. So looking for every little chance to improve the efficiency is essential. This is just an example over here to the left. You see the perhaps newest one from Artemis, the company. Over here, it's in the middle. Again, how it works almost like I often compare it to an engine, right? You have a piston, and then you have an exhaust valve and inlet valve. And by controlling these intelligently, you can increase the efficiency very much. Over here is a drawing of how it would look like if we reconstructed a 3.5 megawatts motor. The operating principle, I think many of you who are working with fluid power will recognize this one, but as there are many electrical people here, it might be a good idea to look a little bit more how it works. So if you have a motoring system here, that means that you put in high pressure and would like something to rotate. You see, you don't have here the piston. You have a high pressure manifold where the red one is high pressure, and you have a valve to tank. And then as the piston moves up here, you see you have low pressure here, so it can get out without any pressure drop. And in fluid power, we have that the flow multiplied the pressure is power. So if there is no pressure drop, there's very, very little losses. So that's the main idea. But then as you go nearer up here, you close before you open the high pressure for the low pressure. And then of course, when you have closed this one in a small displacement, the pressure will increase. But when it's at the same level as the high pressure manifold, you then can open and put in some high pressure volume, and that will put down the piston here. And then you close again, because now you need an exhaust stage. And then of course the pressure will drop, and you are able to put it out again without any pressure drop. So that really is can get a very high efficiency, and also of course you don't get these very high pressure drop across the orifice that can involve cavitation and make it sound like a machine gun. So that's the main idea. The idling cycle, of course, is when you don't use a piston. If you have many pistons to want a certain amount of flow, you might not use every one of these. Then of course you just have an open valve to a tank all the time. Yeah. But what are the desired valve characteristics? Because the valve characteristic to open these valves, of course, will be a kind of actuator. It should be compact, low input power, fast switching compared to piston cycle, and low pressure drops. That's the main idea. And we have looked at different ways to do this. This is just an introduction. I think it's something about, I think we will skip that one, the historical part, how it has developed from the 1980s. And here are some attempts for where we could use this kind of transmission. The most newest one is that, of course, that the Danfoss company, Danish Danfoss company, has bought Artemis, who actually was the leading part in having these transmissions, and they're now building some companies in England to produce it actually and put it in some these small vehicles. It'll be interesting to see when we have these on the market. This is actually a little bit just the same again. And again, to ensure the advantages. I don't think there is any disadvantages. It'll be a little bit under control, so really should focus on developing this one. But of course, one can imagine that when we have low speeds and low displacement radius, we will get some more ripples and so on. And I think that those that are working this are still struggling with some of these. So the technology is still immature, even though on some web page you can see now it is there, but you can't buy it actually. So there are some problems still. Here are some valve design topology to if you go into some of these machines we have, you can see the size here, about 50 millimeters, and these are very compact, these integrated, and you can see the red one down is actually the piston. It has this shape because we have to look into the different flow-induced forces that will that will be inherent here in this design. So we will need a fast movement, low power and low flow losses, and a very small size. We have looked at some PhD projects in a moving coil actuator, and you can see some of the benefits to the left: possible decrease in active power, decreased and bidirectional force capability, but the challenge is the permanent magnets and coils subject to high pressures. And then the wire connection is because these switching times are very high, and if you want that to last for 20 years, it puts some huge demand on the wire connection. It's not that easy to do this design actually, because there are many conflicting requirements. It's just given an example of some of the things that is needed in making an optimal actuator. And of course, you can use here again a valve optimization. Here we had 10 parameters and some constraints in, and then you can get an idea of all the parameters that describe the actuator, and get here a Pareto optimal front and find out which design should we choose. And that needs to be done for each actuator. Here are some of the results, and you see the size of it. It's an actuator here, and it really shows superior performance in comparison to conventional valves in fluid power switching valves. You see we have 2 millisecond switching, 350 bar, and that the pressure drop at 125 liters per minute is only 0.6 bar, and that's very, very low. Here are how they are mounted. I have to look at the time. Oh, time is running. So we have, of course, built in our lab some experimental test facilities, and we also have compared with, this was a moving coil actuator, but also with a moving magnet actuator. And you can see in this diagram up here some of the advantages, disadvantages, but the performance parameters are almost in the same range. Quite now we are looking at a solenoid actuator also to compare it. Now we come to the control strategies, and that's more, of course, you internally for the individual actuators have a control part, but you also have what we call system-wide control, where you actually have to control the whole transmission, and that's two different things. Here we see from the DG motor you can have a full stroke, so every revolution put out a certain amount of flow, And then, of course, you can couple some of these actuators in and out. But you can also have a partial flow here where you cut as updated once per revolution, and you can have a sequential flow. But these of over here, you still will have to live with that you might switch at higher pressures. So it's not that ideal, but it can be used at least at low speed. So here are some of the control challenges we have. And also for the wind turbine, we don't need to operate in all quadrants. But if you look at a general transmission, that is necessary. Suddenly we don't have a control time schedule that is monotonically increasing. And the control decision of multi-machines are taken at different times. And you see that you can actually, if you model this as a complete system, you will perhaps in the same system have different sampling rates and so on. And that's quite complicated for people who know something about control. You can, of course, make a continuous approximation, but again, you will have the eye frequency and delay time is depending on speed of machines. But of course, you end up with something that is well known, but there are some disadvantages here that you don't take into account. Then you can go and make a completely discrete approximation, but you will have the same again, and the eye frequency and delay time is dependent on the speed of the machine. So what is the solution? Sorry. Well, what we have tried to do is to look in what we call a hybrid dynamical model. It's a very nice approach that can easily model some of these systems here. And we actually have a continuous and discrete effect. So that was a good approach, but I must say that we have used a lot of effort in it, and it's quite complicated. Up here, the x dot, for example, could be the velocity of the states, and x plus down here is the who represents the value of some instantaneous shift. So you can define these jump sets and so on, and they could be, for example, up here, if it was a ball hitting the floor, it could be something related to position gravity, and down here there's a d here, the discrete jump set could be something if the position of this ball hitting the floor is equal to 0 and the velocity is less than 0, you can model it on this one. So it looks nice, but you only get a model. Then that can describe some of these effectors for current control, but when you have this model, you need some control, and there will typically be some Lyapunov stability control concepts. And as you know, there's no way to do that. So that really needs something to be creative. And also this, it easily becomes so complicated that you have to make simplified models. But what is then the advantage of having a hybrid if you go down to a simplified model and then you can model it as hybrid? So here really are some research, and we will be looking into that in the future. But the analysis shown here is that you cannot always take out the dynamics. Until now, it has simply been mostly open loop ways to do it. But it has been shown in more than one study that sometimes you really have to look into dynamics. I think I might skip this one because it's also a part of when you have different topologies for these motor and pumps designs, which one to choose is the best one. And the problem is nowadays that it could take a whole project just to take one of these and analyze it. So there has been a lot of research going about to make some CAT and integrated analysis tool, and that's got something we have looked at is isogeometric analysis. But I will not go into this one here. A little bit about pump control drives, because I guess that's also the future. If you have to look at valve control drives, the losses might be too heavy to compare to many of these electrical drives. Of course, we still have the advantage of having this linear movement that is more difficult to get out of electrical drives. But here are some overview from one of our PhD projects about some different concepts considering pump control drives. And you can see to the right over here, there are some of these things. all these elements here that one of these drives should satisfy, but it's difficult to find one solution that really satisfied all these. This is just 2 examples of how they can look like with a speed variable and a fixed. Here you have a fixed speed, and here you have a variable speed. Different concepts that have been looking at. There's another project that was actually initiated by one of our researchers to look into is it absolute? Can we do this? Because it looks like it'll be a very expensive one when we have all these pumps and motors. But you're utilizing very simple, cheap pumps and motors. It was actually possible to make a small project that showed that there is something in this one. You see it down here on the figure here. Of course, ideal, you could match the pumps and motors to the area, but that is never realistic. You will have cavitation or the pressure will grow. So there is a small extra little pump in here so that you have a difference here, but you always assure that you have access flow, and then you can throttle these ones. But if that's not a big amount of energy you're losing, there could be something in this. And the results here is just something about the experimental build-up and testing in different loads in some areas and compared to a conventional system. And here you can see some of the energy efficiency advantages. You get almost the same efficiency, but if you have recovery, which is much more easy to make here, you will have, as it states here, 57% higher efficiency brute, and a high speed is 69, and that's something one must say, right? It's really, really a high percentage you can increase it. What about the price then? Well, these guys also compared that if you should have a drive, a 4-cylinder axis driven by this new concept, and here are some of the requirements of the velocity and the force, then what it will be looking like over here to the right, if you should do it with standard components, and over here if you should use it with these components that was in the test. And here the savings here, you can see down here that the savings total after first year is actually 8,000 euros, and that's impressive that we can actually build this one by standard components already today. But of course there are some ideas, I can just say them here. If it should be really competitive, there are some things that we need to look into. And then a new project has been started up called Sendrai that aims to contribute to this, but two are the main objectives that we can see here. For example, the load holding capabilities. And here are the way that it's built up. And it's actually, let's see if there's something here. And here are some of the things that it can solve. And you can also, for example, change the stiffness of the system by using this one. So actually it looks quite simple. And I guess now they are working on it together with Bosch to see if this is realistic. And I think it is very promising results. But again, as I say down there, always focus on the business case, and that's the way it is. Here are some of the performance parameters. I'll not go into that. And then, of course, if you look at this DDP technology, we really need to look into reliability fluid power technology. And I mentioned that in the start, that this is being a big research interest for us right now, because if these should be comparable and live for 20 years, we really need to look at this one. So it's not only just a few years ago, fluid power was only a mechanical component, but now it's really, really a mechatronic component. So of course we need to go into this. And the conclusion here again, but I think that one of the most important things is to understand the user's needs. Understand that the machine operator is part of the machine. We need some demonstrators, consider cost, controllability, and safety. Two different, for example, if we take a loader machine, this is really, really important. Two different machine operators can have a completely different feeling and so on. And even though you put in a very smart actuator in one of the axes, But if it only runs for minutes every day, it might not be necessary to consider it. So we really have to look at the full machine to get it into the market. For fluid power to be comparable, we also need to recover potential and kinetic energy. Otherwise, the efficiency is simply not good enough. There are some different ways to do it. Common pressure wheel systems, pump control system, and digital displacement technologies that must really go into it. And then, of course, reliable fluid power technology is an area of research. That was actually my first part, but I think I will have, if I can have 5 minutes. We have been looking for, has gone into here and will go for a big application for hydraulic for exoskeletons. And it's together with actually people in Tampere, Professor Linyama, and also guys in Linz, Professor Rudolf Scheidler and Bernd Winkler, and one of his colleagues, Latner also. And they have a project running now that we are part of, and we will go for some extra funding looking into this one. And there are really some challenges and opportunities for putting fluid power into the actuator part. Of course, we know that it's the aging society we have, so this will be to keep up the mobility of people. It has more and more attention putting into these exoskeletons, not only for sick people, but also for healthy people that are having a heavy job to do. This is just some of the how the early expenses are for these people. And this is the increase in publications that have the interest in exoskeletons. So it's increasing heavily right now. And but there are some challenges. There are, for example, the actuators, and there are the brain-to-machine communication and the mechanical interface and intuitive control. So it's really a transdisciplinary, and there are some really, really huge problems to get a fully working exoskeleton. So there's a need to develop compact efficiency and high power density actuators. But the fluid power has the potential, and I think actually there's a paradigm shift to throw away the electrical actuation and put in some new actuation concepts. But we have to combine it with sensor and biosignal processing, movement analysis, and lightweight design and smart materials. So again here, new actuator technologies, but we'll put focus on optimization. These are something that are said here. Optimize structural components, the coupled dynamics of human body and structure, and low energy consumption and ease of control of motion. So we really need an interdisciplinary group to work on this one, and that's why we both have Finland into it, and which are known for developing very small actuators, but also the guys in Linz in Austria, which are experts in also these actuators, and they have started the project here. This is some of the things that we need to put into the small fluid power, and here is the first trial, and it's actually being built down there right now, where we look at the knees and put in the multi-chamber cylinders with some switching valves to keep up the efficiency. Here you can see some of the comparison. This drive that are typically used on the knee is the one to the left, 1 kilogram, and but dimension is very huge. And if you can go in to the right and have a cylinder, it will only be very small. These are some of the electrical devices that we can use today. And down here, we see that this is the fluid power one here. And it really uses this digital cylinder solution. So no throttling. This is more into detail. I'll not go into it. This is also, and here it's how it's implemented. You can see to the right over here, if it's an electrical drive going around with these one here, big electrical motors is not very appropriate. But of course, you in the backpack needs the same amount of power, but you will remove the weight to the backpack. Yeah, But the disciplines shown down here is the biomechanics and motion control, energy storage technology, lightweight design, and materials. There'll be a lot about new materials. Who said that it should be iron? It could be plastic. So if you can change it every week, that might be an idea. So here also comes some research in. But it has this fundamental strongholds due to force power density. But they really need some research to do this one. But that'll be in small actuators. Okay. Sorry if the time was running a little bit away from me, but thank you for listening, and that's it.
Thank you, Torben, and sorry for the misunderstanding and the mismatch with the scheduled time and the planned time. And thank you for your effort to fit the talk in the time. I think we have to move to the next speaker. And okay, so the next talk is by Marcel Schuck. He's a pioneer fellow in ETH in Zurich in Switzerland. He's with the Power Electronic System Laboratory and working on different aspects of mechatronic systems. And he's also CEO and co-founder of the private company, No Touch Robotics. So Marcel, thank you, and thank you for waiting also, and thank you for your talk, and the screen is yours.
All right, thank you very much, José, for the kind introduction. Good morning, ladies and gentlemen. Warm welcome also from my side. As already mentioned, I'm here in a few functions today, but the main function is as the Pioneer Fellow of ETH Zurich, where I'm also a postdoc at the Power Electronic Systems Laboratory at ETH with Professor Johann Kohler. And talking today to you, I want to talk about several aspects. I've structured the talk a little bit into the aspects of showing you first where we come from, what we do, and then I'm going to transition with this background to this, I would call it rather provocative title, Contactless Gripping, Paving the Way Towards Flexible Micromanipulation. I want to cover what is contactless gripping and how does this actually work. So let me start with this overview here. So as mentioned, I'm part of the Power Electronic Systems Laboratory. We're part of the Department of Information Technology and Electrical Engineering at ETH Zurich. I guess I don't have to say that much about ETH Zurich here. We're continuously growing, becoming bigger and bigger with more professors being recruited. Also in this area of electrical engineering. And within this Department of Information Technology and Electrical Engineering, we have an energy research cluster consisting of a variety of professorships. And the one that we're dealing with at the Power Electronic Systems Laboratory is on the one hand, obviously Power Electronic Systems, but also on the other hand, advanced mechatronic systems. So everything that is related to energy conversion, electrical to electrical, but also electrical energy to mechanical energy and vice versa. This is well embedded into the fields of power systems, high power electronics, high voltage, and semiconductors. And usually we try to strive for a balance of fundamental and application-oriented research here. If we look at the research scope of the Power Electronic Systems Laboratory now specifically, on the one hand, we have the big topic of power electronics, but then also a lot of interdisciplinary projects together with the Department of Mechanical Engineering in the fields of turbo machinery, but also in robotics, which I'm going to talk to you more about today. But then also microsystems, shrinking systems, getting to high power densities, low weight, low volume, and in a variety of applications such as airborne wind turbines, microscale energy systems, wearables. We've heard it in the talk before that it's important to have lightweight actuators here, exoskeletons, artificial muscles, as we've heard before, and then also things related to pulse power. So let me start out in what we do in the areas of mechatronics and electric drives. As mentioned in the 2 previous talks, thank you to the previous speakers for the kind introduction into this field. So mechatronics is basically the combination of having actuators, the contributing electronics, the control theory necessary to control these actuators, as well as the entire software or firmware part related to this. And I've brought you a few examples of our research here. You can see, for example, a power converter that is intended for lightweight conversion in the area of airborne wind turbines, for example. Then we've done a lot of research on linear mechanical actuators, but also in the area of high-speed drives, which I'm going to talk to you about a little further here soon. Of course, the control of these devices all require rather precise sensors. And the smaller the systems become, the higher the dynamics of these systems become. We also require high-speed signal processing, which has in a large portion of our research moved now to FPGA control in order to get the bandwidth necessary. So you can see that most of the key components are available today, and we have for these systems an extremely wide area of applications. And the question now is to find the best setup, the best combination of these individual mechatronic components in the relative application. So I want to talk to you briefly about one industry trend, which is achieving high power density. We've heard it in the previous talk from Professor Andersen already. And how do we get to high power density for electric drives, for example? If we look at the scaling law, the scaling laws of such electric drives, you can see that the power density is increased for higher rotational speeds. Of course, there are some limits to these, to the rotational speed, mainly given by the bearings that I need in this area. But I've brought to you here a short overview of power on the x-axis here and rotational speed on the y-axis, and you can see mainly 3 areas that are coming in and pointing towards sort of this tip of the triangle here in this area, which is on the one hand, if I want to drill very small holes for surgical or dental applications, I need very high rotational speeds required by the application. Then for PCB drilling at a little bit of a higher power level, the same thing. And then from this area here, we have coming the applications in areas of industrial gas turbines, microturbines, and compressors. We, for example, worked on a project that was about cabin pressurization for the Solar Impulse airplane, where weight was a major concern. And as you see here, there are quite a few prototype systems that we've built up at the Power Electronic Systems Laboratory in close collaboration with our spin-off Celeraton. And one of the research that was carried out here, for example, was a 1 million RPM, 100 watt rated power system that you can see here. So it's got a rotor diameter of 3 millimeters. And you can see quite a compact system for 100 watt of output power. However, this system still being suspended by normal ball bearings. We had very high losses in the bearings here. And again, this targeted at applications in microscale drilling, dental technology, but also for rotating mirror systems. There are quite a few application areas. So the next logical step for these high-speed machines for us was to go and move towards magnetic suspension, for which you can see a prototype here, a system that was capable of reaching 500,000 revolutions per minute using a magnetic bearing. And you can still see it's a long cylindrical shaft rotor. which makes it quite complicated to suspend this magnetically because we need to stabilize multiple degrees of freedom here. For once, we need a radial magnetic bearing at each of the ends of the machine, each of the axial ends of the machine. And then we also need a suspension that stabilizes the axial direction, which is this damping coil that you can see here. So this is the cylindrical part that is inside this machine. And corresponding to all of this, we also need suitable position sensors, meaning that we need to detect the position at all the areas in which we want to control it. And a typical application for such a system, for example, could be a flywheel application or reaction wheel application for small satellites in order to control the attitude of such satellites. So as I mentioned, in the area of magnetic levitation, we quickly arrive at concepts or topologies that are highly complex, mainly owing to the fact that if you look at this graph over here, these systems are passively unstable, which means that if I want to levitate a rotor, I always need a sensing system, and I need a position feedback control, which is usually then also combined with a current controller. So we have a two-stage control approach, a cascaded control. So I need all these components, and especially if I'm moving to very small components, the sensing becomes challenging, and the bandwidth requirements, as mentioned earlier, are very high. We all know there are also approaches related to passive magnetic levitation, such as this one, where I have a rapidly alternating magnetic field that induces eddy currents in a rotor. And then by the interaction of these external magnetic fields and the eddy currents, I get a repelling force, with the drawback that this is also combined with high losses. And I cannot implement usually a damping, but only a restoring force, which increases the stiffness of the system, but does not give me any damping. So we've looked into alternative approaches of making things levitate or suspending things without contact. And I came across here a very interesting concept, which is acoustic levitation, which you can see visualized here. You have an array of acoustic transducers down here. You have a pressure distribution that is generated, an acoustic pressure distribution by these transducers. And within this acoustic field, you can levitate small particles that are smaller than the wavelength. The big advantage here is these systems are passively stable, so I can, in an open loop fashion, generate this acoustic field. I have relatively low losses compared to something like this, where I have an alternating magnetic field and eddy currents. However, the load capacity compared to a magnetic bearing is relatively small. And going into more detail of how this works, these pictures, by the way, are from, I would say, the pioneering paper in this area that was published in 2015. By Asia Mazo, then at the group of Bruce Drinkwater in the UK. And as I said, we're using arrays of ultrasonic transducers in this case, and each of them are controlled separately. So we have a separate signal generation and a separate power electronics for each of these transducers. And if you look at such a transducer model, you can model them basically as a piston moving very rapidly, in this case at 40 kilohertz up and down. And the pressure distribution that you obtain above these transducers or above these sort of bowl-shaped transducers array is the sum of the individual pressures contributed by the individual transducers. So the part that we can influence here for every transducer individually is, on the one hand, the phase, which means when does the acoustic wave arrive at the position that I want to levitate a particle, as well as the acoustic power. And this gives us a lot of opportunities to precisely shape the acoustic field above these transducer arrays in a way that we desire it here. You can see all of this being expressed by these equations. And what you can see here in the image is basically how you can now, by adjusting these pressure distributions dynamically, you can move a component, for example, along a trajectory here, varying the X and Z position, or different trajectories as shown down here. And you can also rotate a particle by rotating an acoustic pressure distribution. So this was the part that caught our interest at first, because as you saw in the slides before, we're very interested in reaching high rotational speeds. So we made a first attempt here, and in order to make something levitate and spin, you need to select the correct acoustic trap. So there are basically three basic types of acoustic traps, namely the twin trap, the vortex trap, and the bottle trap. Some of them have their analog parts in the area of optics, where you also have waves that you can give a certain phase signature to. But you can quickly, if you look at the pressure distribution pictures here, or even here in the three-dimensional picture, you can quickly see where their names come from. So the twin trap is basically two areas of high pressure with a low pressure area in the middle, and the particle being suspended in this low pressure area. The vortex trap is almost completely symmetrical in the circumferential direction, and the particle is sort of suspended in the bottom of this well. It's called a vortex trap because if you look at the phase signature, you have a rotating phase signature, and this then also causes the trapped particle to start and rotate. And the bottle trap, if you look at it, it looks like the particle being suspended in the bottom of a bottle, or laying in the bottom of this bottle. For our first experiments here, we have chosen the twin trap because it provides sufficient load capacity for lightweight particles, meaning in the beginning we use styrofoam, but it also offers the opportunity to rotate particles and has a high radial stiffness. So one of our first setups looked like this. Again, we have an FPGA to generate the phase signals that we desire. We have a power electronics board that goes on top of this FPGA. We have a setup that arranges these ultrasonic transducers in the circumferential direction, all such that they point at one single point. And at that single point, we then have, in this case, a small styrofoam particle levitating. Here again, you see symbolized in 3D the pressure distribution. And by now rotating this pressure distribution, we can make the particle rotate. So how do we do this? In order to generate this type of trap, we have a phase shift of 180 degrees between the two circumferential halves of this setup. And we just shift this and rotate it around the z-axis, and then the particle follows this rotation. This was the second setup that we built in order to achieve this goal. You can see here basically a sphere with the pole caps being cut off, and all transducers point at the center of this sphere, where then a particle is levitated. And again, we have our excitation electronics that is controlled such that we can rotate this phase shift that we separate here with this symbolized plane around the z-axis, which then causes the particle to rotate. With this setup, we were capable of reaching 216,000 revolutions per minute, which then bears quite a few other challenges, such as that you are now shifting the phases of the control of these transducers so quickly that you excite other frequency components other than their main resonance, which you can see here. If we look at the impedance spectrum of these transducers, you can see several resonances. Usually they're operated at the resonance at 40 kilohertz. However, if you now have this additional rotation, you excite other frequencies, which then cause other resonances to be excited. If you look at the transducer model, you can basically, it's a piezoelectric transducer that you can model then with an equivalent circuit with multiple serial resonant paths. And you introduce one of these oscillator paths here for every resonant frequency. So quite a high frequency, or quite a high rotational speed already here. We'll see in future experiments if we can still increase this. But what we found also very interesting is not only spinning things, but really using this acoustic levitation technique to grip and manipulate objects in general. And here mainly in the area of very small and fragile objects, with one example being the assembly of smartphones. Here you can see a picture of the Foxconn floor of how these smartphones are still to a large part assembled manually. But then also, of course, coming or being in Switzerland, watchmaking is a big issue here. So there also they need to handle very small and fragile components. And the big challenge here is that if you grip them on a contact based with a conventional gripper, such as shown here, you can only use a fraction of the surface area of these components to really apply a gripping force, which is symbolized here. So here you generate sort of a friction grip, or you embrace part of the component with the gripper. However, it's very difficult to really use the entire surface area. So for this, we've developed a solution, and now we're making this transition to no-touch robotics, which is a spin-off of ETH Zurich and of the Power Electronic Systems Laboratory, where we're exploring the possibilities of handling components in a contactless way. So here you can see one of our first demonstrators for this. So we have a rather cheap robotic arm, and then we have this gripper mounted in the front, where you can see two pole caps now, with the center or the middle of the sphere being left out. All these transducers focused on one point. And for example, here you can see a metric 3mm nut being levitated in this acoustic field, completely without any mechanical contact. And another big advantage is if I don't have to touch anything, I don't damage its surface, and I do not contaminate the surface. And the interesting part here is now also that I am not limited anymore to a certain geometry, but rather I can grip a wide variety of geometries with the same gripper. In order to use this now in applications in process automation, it's necessary, of course, also to insert and remove objects from this acoustic field. And the way that this works is there are several approaches. Here you can see again our system consisting of the control, the power electronics, and then the levitated part. And I have a short video here. So here you can see how an object is gripped from an acoustically transparent surface, and it's going to be put back down on the same surface. So this is the rather easy part, I would say. But then we can also manipulate the acoustic field by moving, by changing the excitation of the transducers, and thereby moving the suspended component, as you can see here in the middle. A part being moved without any mechanical movement. And then here the single-sided picking, again, from an acoustically transparent surface. But in the next slides, I will show you how it's possible also to do this from acoustically reflective surfaces. And this just as a quick reminder or hint to our paper, automated insertion of objects into an acoustic robotic gripper, here at this conference. So if you have a few minutes afterwards, please feel free to look at the paper. And again, you can see here the case with the double-sided acoustic gripper and the acoustically transparent surface, different gripper arrangements here consisting of a cylindrical surface and also a lid that has transducers on it up here for single-sided gripping. And the interesting part here is how do I get such a component into the gripper and pick it up from an acoustically reflective surface. And in order to study that or come up with a solution for that, you now, of course, need to also consider the reflective part of your acoustic wave acting at a certain point in space, X, Y, and Z. And to study at which points we can actually levitate an object in a stable manner in the presence of an acoustic surface, we now need to consider the maximum attainable pressure for each point in space, meaning that if I get a destructive interference between the direct acoustic wave and a reflected wave, at a certain point in space, I have no opportunity of levitating apart there. And you can see this illustrated here. Again, imagine this cylindrical gripper with the transducers on the top. You can see if I have no surface present, I have a maximum attainable pressure distribution with a rather low gradient. However, if I now approach a reflective surface down here, I get very strong gradients with a minimum at 1/4 of lambda, the acoustic wavelength, which means that in this case, I can basically only trap a particle here in this part where I have a minimum of the attainable pressure distribution. However, if I now use transducers, so this basically being a standing wave between these transducers and the reflective surface. However, if I now additionally use also the transducers coming from the side, you can see that I can lift a component also beyond this minimum here and move it upwards away from the surface. And then eventually I can remove the whole gripper with the robotic arm. This being also illustrated here, and these all being figures from our paper. So if you're interested in more detail here, we have that also for download on the website. So here you can see I approach a reflective surface with the gripper, initially generate basically a standing wave between the top transducers and the reflective surface, lift the particle up to 1/4 of lambda. Then next, I additionally switch on the transducers on the side, lift it up a little bit further, and then I generate what we call a vertical twin trap, because it has these two pressure maximums on the left and the right of the particle, and move this up away from the surface. And then at some point, you can see here in the subfigure D, we have basically no influence anymore of the reflective surface, and now we can completely move the gripper away from the surface, resulting in a picture up here. You can see here the force distributions being in the area of millinewtons, so not huge. Again, this is mainly intended for small and fragile components. And you can see the force distribution of these individual trap types here, and can see that they have sort of this zero crossing with a negative gradient where I can levitate something at different vertical distances from the surface. This can also be used for liquid handling. So if I have an acoustic field that generates pressures on the surface of something, I can use this also in the area of liquid handling. Here you can see in this short video a droplet being levitated and moved vertically here in a closed loop manner with a camera that tracks the position. So again, I can combine this with closed loop control, just like magnetic bearings, but I don't have to. And here you can see something, this is the last application use case that I want to mention here. What we've seen so far is manipulation in the millimeter scale or millimeter range. However, we can also scale the system down to the area of several tens of micrometers. And here's a very interesting area between 20 micrometers and 100 micrometers, which is the size of cells, biological cells, human cells. And here oftentimes we have the challenge that we have just an assembly of cells on a Petri dish, and we need to sort these cells, for example, by vitality, by cell type, according to a certain biomarker. And the challenging part here is that today this is done either by glass capillaries, where then the cell that is supposed to be selected is aspirated and sucked into this capillary and then released somewhere else. Very time consuming, very high training effort here. And then a different solution here would be to use needles that are attached to micro positioning tables to move these cells. However, still a very slow, painful, and unreliable solution. very difficult to replicate this in multiple experiments. And in these cases, always we have the issue of cell damage and contamination. So this being symbolizing this sorting of the cells. Also for this, we've developed the first prototype looking like this. So you can see a standard microscope, inverted microscope, light source up here, the objectives lenses down here, our acoustic actuators up here, the power electronics next to the positioning table. And then seeing the whole thing from the bottom, you can see the glass slide on which you have a droplet with the cells or your sample in suspension. And now we generate a pressure distribution that is then used to move these cells. Here I have to mention as a disclaimer, this is a first prototype. In order to really get selectivity on a single cell level, we need to move to different transducers here. This is very much work in progress currently, but this was sort of our first demo system to verify that this manipulation is actually possible. And then the interesting part is, again, here you just have sort of a 3D mouse manipulator in your hand, and by this you can shift the cells and the components basically in all degrees of freedom, just like you would move a CAD model on a computer screen. So the handling is very easy, and it's very easy to get repeatable results here. Again, other ranges of applications that we see for this technology. I've covered micromechanics and watchmaking. I've covered a little bit of life sciences. Looking at the semiconductor industry here, oftentimes, as we've heard in the first talk, also the precision requirements are very high, so we're not yet sure if we can really fulfill this. However, again, here also very promising because there is no mechanical contact, there's no particle generation, so this is very suitable for clean room environments, improving quality and yield because there's no handling inflicted damage, no particle generation. And again, you saw it in the liquid handling case. If I now have liquids that are hazardous, such as concentrated acids, I can handle or suspend them without contact to a surrounding container. And with this, I'm already at the end of my talk. And here coming back to the magnetic levitation. And I'm very happy to answer questions. Thank you very much for listening.
Okay, thank you, Marcel. Thank you for your nice talk. And now the presentation is open for comments or questions. I don't see anyone from the audience, but I can ask you something in the middle, in the meantime. So, which is the effect of the shape and size, maybe mass of the objects or the particles you are manipulating on this levitation application?
Yes, so as I said, I mean, it's mainly intended for very small and therefore also lightweight particles, so in the range of up to a few hundred micrograms. However, if you look at millimeter scale objects, they're usually rather lightweight. And size-wise, we're limited by the acoustic wavelength at 40 kilohertz in air. This is about 8.5 millimeters. And so we're limited to about half of that, such that the component that we want to grip fits into this acoustic trap that I've shown earlier.
Mm-hmm. And does it depend on the transducers you use? I mean, these were commercial transducers with a given size and power. So, did you try any different elements for manipulating different objects?
Yes. So if you want to move to bigger objects, you have to go down with the frequency. Of course, you're limited somewhere there that you remain in the non-audible or ultrasonic range. But we've also explored, for example, 25 kilohertz transducers, and then you can suspend bigger objects.
Okay. Thank you. So if no any further question, thank you again, Marcel, and we move on to the next presentation. So Tatiana,
Yes,
would you like to?
our next presenter is Professor Yongling Fu. He's a currently professor in School of Mechanical Engineering and Automation at Beihang University, China. He obtained his PhD in 1993, and from 2000 to 1998, he is a professor. His research interests include actuators, hydraulics, mechatronic system, and control, and he have extensive network with the companies and university, and have been very active member in a lot of R&D and international and cooperative kind of projects. And Professor Fu will give us his talk on topic new actuation and transmission solution for aerospace application. Professor,
yeah,
you can take over.
oh, thank you. Dear ladies and gentlemen, it's my pleasure to give these lectures. And good morning, maybe in your side, in my side, in fact, it's dinner time in Beijing. And my topic is about new actuation and transmission solutions for aerospace and defense applications. My name is Yongling Fu, and I'm from Beihang University. I will give this introduction from these three sides. As you know, sorry. Sorry, I give the fourth PPT. I will change another one. As you know, more electric aircraft and powered by wire were proposed by United States and Europe in 1980s. And the electrohydrostatic actuator, EHA, has been successfully applied on A380 and F-35, then on A400M, A350, and GW600, etc. In A380, the EHA has been applied for EBHA, for elevator, for ailerons, and all 24 servo control per aircraft. And on F-35, all main flight control surfaces are driven by the EHA or EMA. This is F-35. And after the A380, A400 military wire has also used the more electric aircraft architecture. And after the A400M, A350 has used more EHA technology. EHA is becoming one of the main forms of next generation of aerospace and actuation systems. This sketch is the principle of EHA. It uses servo control motor, electric motor, to drive servo pump and then regulate the servo cylinder. And these valves is only for functions. And the electric motor controlled by controller and this servo driver. This is the typical EHA principle. And this side is about the IeCAT structure. It's mainly 4 parts. One is motor pump unit, and this is hydraulic cylinder. And this part is about manifold, including reservoir. This is reservoir. And the 4 part is mounting plate. This is typical modular design. The parts involving hydraulic passages are additively manufactured, including the mounting plate, this part, for connecting different modules and the manifold for integrated valves and sensors. All these valves integrated in the manifold. A balance between performance and cost can be achieved. This is another study case. This is a artillery. Generally, this gun is regulated by servo hydraulic actuator SHA. For example, T90 gun pitching control uses SHA. SHA is a servo valve, and the servo valve has high cost, easier pollution, and low energy utilization rate. The oil tank is larger in both size and weight. Hydraulic oil combustion will bring secondary damage when heated. And in M1A2, gun pitching control system used electromechanical actuators like this. Is electric motor, gearbox, and ball screw. This actuator is very simple, but the problem is in both stack and heat dissipation, and fatigue damage is likely to occur. So in Actuator, EMA is not very popular. So for artillery, we need a new type of actuator. IeCAT combines the advantages of electric and hydraulic actuation. We applied it in tank gun control system to improve the performance. Use this. And the principle is also like airplanes, fuels, but it's more simple. IeCAT uses closed local hydraulics source like this, and realize distributed hydraulic actuation as well as the same performance as SHA. Is less leakage, lower energy consumption, smaller volume and weight, higher reliability and efficiency because we do not use the servo valve. And we realize the power by wire and easy to install and maintain. It's also have the large output, self-lubrication, good heat dissipation, no stack. And the IeCAT has its own weakness also. For example, difficult control because the electric motor and the pump is high power and the lower responding density, lower precision accuracy, larger end installation size. So we need to introduce novel sliding motor reservoir and virtual law. In past 20 years, we research many controllers. Sliding mode controller is very well, and it could get chatter separation, unmeasurable states. So it's a good way for EHA control. In artillery EHA, we developed the prototype like this. And also we developed the test bench and use the sliding solid mode controller. This is a very simple one. And to get a sensitive factor from delta 0.1 to 10, we do some research work. And we get this step representation. This is a good way. No, this, and also very fast response. In the research position, we also realize that the EH's size and weight also too high, and we need to use the additive manufacture. For example, for legged robots, SHA use this method could reduce the size and optimize the flow rate. In EHA, the manifold, the mounting plate, this is traditional machine method. It must, this method, let it pass the pipe to connect each other like this way. And use the additive, we could realize the pipe like this. We can reduce many of these connection passages. And the manifold use the additive method. We could get this, and the mounting plate like this. We could reduce 20% the weight. And the passage shape could also be studied like this. Elliptical and teardrop shape are used, but no apparent pressure loss advantages according to CFD. In EHA, the key component is electro-hydraulic pump. As you know, the development of the urban hydraulic system is mainly towards the following aspects: high power density, high pressure, and weight payload, intelligent, etc. This is traditional one. Electro pump is electric motor to drive the servo pump using the coupling to realize this hydraulic center. And electric hydraulic pump is a new type of the integrated one. It integrates motor with the pump and the valve and the tank and the sensors. Like this, we let the rotor, the two components rotor to integrated one. And we does not use fan again, but we add the tank, oil tank. And no coupling. Let the pump's rotor and the electric motor's rotor like this to integrate one. And the shell with the same one. So the difference between the traditional electric drive pump and the electrohydraulic pump is the difference. More smaller, more lighter, more maybe cheaper, and no leak. And the integrated design with drive support and flow, we have these 4 types. Like this is a motor rotor, and this is a motor rotor, but this way is directly drive the pump's cylinder. And this is from this plate to drive the pump's axle. This like this, and this like this. This integrated type of electrohydraulic pump deal with flow field, heat flow couple, and the magnetic field, etc. We must carefully simulation. From input to output, the energy transfer is from electric energy, mechanical energy, hydraulic energy. So based on the way of energy conversion, we must build a comprehensive simulation model of electromechanical and hydraulic control in AME-SIM. We do some research work. We find that along with the increase of the rotation speed, the loss of hydraulic one between the rotor and the shell and of the electric winding, the oil film will produce more losses. These 4 kinds of electric hydraulic pump is prototypes. This one is a brushless DC motor to drive a axial piston pump. This is parameters. The research result is at this parameter, 28 megapar, 7,500 round per minute. The efficiency is about 66%. And this is a 3-phase synchronous electric motor with a plunger pump. This is the test results. And this is integrated hydraulic power source. This is parameters. Along with the integration research work, we find that for IeCAT, the pump is very important. And IeCAT, especially for the aircraft, we need high ratio of power to mass. It must have a high speed and high pressure of axial piston pump for IeCAT. And this kind of pump will bring great challenges to the structural design and material selection of the friction interface of piston pump. So we set the research work for the axial piston pump. for the 3 friction pairs. From design, we should consider this leakage, friction, damping, and heat. We must consider load condition to realize high efficiency, less heat, and lightweight. This is very typical V-shape design flow. This kind of design method could combine of component and system design with simulation combined with manufacturing, reliability, research and development cycle are optimized. Research is based on key components of pump. As you know, in the axle piston pump, there are 3 very important friction pairs. This is slipper piston pair and slipper piston assembles. And this is cylinder block valve plate interface and the piston with the cylinder block. The key technologies deal with load analysis and the pump simulation technology. Test method for pump unit and components. Experimental study on pump parameters and the typical load. Structure and performance optimization. This is according to the flat duty cycle to analysis of IeCAT pump load. This is use AME sim to modeling the axle piston pump, mainly to focus on piston simulation, cylinder block valve plate, and the pressure simulation. We also developed some test bench for the axle piston pump. The load simulation test rig and the friction test results is that we developed some kinds of coated materials and find from friction coefficient this kind material coated valve plate is about 50% lower than that of the nitrated one. From wear height, this coated valve plate is about 12 to 14% of the nitrate one. From wear form, these are abrasive and adhesive wear, while TIL ALN coated mainly adhesive wear. So from the long lifetime and high efficiency, this is a good coated one. And in IeCAT, we find another component is also very important, is a reservoir, like this. Reservoir maintains the pressure on pump intake, avoid cavitation of pump. We developed this kind welding bellow one. Is a kind of metal pipe which is made of many thin hollow diaphragm shaped by stamping and is highly flexible and telescopic by precise welding. This construction reservoir eliminates leakage associated with traditional piston or blade devices. Welded metal bellows reservoirs provide maintenance-free service, high reliability, and long life. Is said in aircraft A380 is lifetime the same with the aircraft. This is the structure. It has non-contact displacement sensor to measure the displacement of the bellow. The welded metal constructor of reservoirs constitute a boundary between oil and air. This is an advantage from the other two cans. After the developed this kind of metallic bellows mass is very low than that the other two cans, and this is results integrated in the EHA. And another very important component is bearing. We find the pumps lifetime, just as I said, the 3 friction pairs is key pass. And another component is bearing. As you know, existing bearing types like this 4 cans. Deep groove ball bearing, angular contact ball bearing, cylindrical roller bearing, and tapered roller bearing. But we give another very new type of bearing is developed and innovated in structure like this. Is from planetary thread roller screw, and we use the parallel thread. No, not like this one. The planetary thread roller screw like this. And the planetary thread roller bearing like this, no displacement again. Its features and inspiration is this. It subverts the traditional structure and makes planetary motion with multiple rows of threaded rollers. Through measuring and rolling transmission, planetary thread roller bearing is formed. In the field of bearing, the principle of equivalent steel ball, like this, multiple point measuring and power split are introduced. Each tooth surface of thread roller is equivalent to a steel ball, and the thread roller is equivalent to the row of steel balls in transmission. The curved tooth surface of the thread crown is equivalent to the equivalent steel ball with larger diameter, and the bearing capacity is greater. This is the result of between the SCAF and the PTRB. The basic rated load has 3 times. This is the result. The last one is the conclusion. Power by wire is a good way to transport energy. EHA has been successfully applied on A380, etc. The research results show that EHA could be applied into other fields. And there are many key technologies need to be studied, such as pumps lifetime, reliabilities, and design methods, etc. And it's worthy of seriously thinking of the EHA principles, the types of pump, and the deep integration of the components, etc. That's all. Thank you for your attention.
Thank you, Professor Fu. Applause for
My
you.
pleasure. My pleasure.
We had some questions from us. Unfortunately, audience didn't left any questions. Thank you. This is great integration. I mean, there's not so many studies about integrated pumps inside motors, and you show so like great prototypes. I have a question regarding in beginning you was showing about the plates and valves, and you was mentioning that they're 3D printed. I would like to ask how you consider, I mean, is it reliable? There's no any problem with fatigue, and what kind of cost we could kind of estimate for this kind of product?
Additive?
Yes, additive manufacturing.
Yeah. Because in aircraft, generally, we need the size and the weight is very strictly required. And this part use the TI 6AL4V this material, and this mounting plate using this steel, and yeah, and this we cooperate with another manufacturing plant. We give this kind of design result, and they transfer to the additive maps and the design.
Okay, meaning there's so many advantages of printing and 3D additive manufacturing that it's why you select the solution. Okay, thank you very much. It's clear, and thank you one more time.
Thank you, your introduction. Thanks.
Thank you.
Okay, so I think this closes the session. This is the last talk of the session. Thank you to all the speakers in these sessions, and also being the last session of the live part of the conference. I would like to thank also to the rest of the speakers in the previous sessions. Thank you for your effort. I think most of us, we are not ready to this electronic format. So I appreciate the effort that you have all done to elaborate to prepare the conference in this format. So the webinars end here, but the conference will continue online with the presentations available in the web, and you can interact with authors and ask questions or comments. So I give the word to Tatiana, the co-chair.
Yes, thank you very much. It was a pleasure to be with you. One more time, thank you for our keynote speakers and invited speaker. It was a lot of new information and it was great to have you here. Thank you very much.
Okay, thank you. And now this closes the session today, and I give the word to Anna, the member, Anna Sánchez, member of the organizing staff. Thank you.
Thank you, Jose. Again, I would also like to thank you all the speakers and the keynotes they invited and all the participants of the conference. Remind everyone that we will have the recorded sessions within the conference webpage or during this week or during next week, but don't worry because all the attendees will be notified by email. Also, I want to remind everyone that all the accepted extended abstracts will be published in MDPI proceedings papers, and we will also have a special issue. So if you want to know more about it, you can go to our conference webpage, or you can contact us at IeCAT@mdpi.com. So this is the finishing of this session. Thank you again. Thank you, Jose Luis. Thank you, Tatiana, for chairing the event.
Thank you. Bye-bye.
Bye-bye. Have a good day.
Bye.
Nice day.